Okay, welcome back everyone. We are now going to turn our attention to rotational dynamics. So, in other words, what effect do forces have on the rotation of objects? So first of all, we're going to be talking about what is torque and how does a net torque change rotational motion. And we're just going to start with our definition of torque. So torque is the rotational analog of force that causes a change in rotation. So if we think about a force that's acting on this beam that's applied a distance r from the hinge, then we can start to imagine a torque. So we define this r as a vector having its tail on the hinge and its head at the point of application of the force. Okay, so we're going to draw these head to tail, and so the tail of F will go at the head of R. Okay? There's going to be a rotation because of this combination. And in this case, the direction is clockwise. And if you think about this, that means that we have a direction of rotation that's clockwise. So what would you say about the direction of the torque? And so I invite you to think back to the right-hand rule from rotational kinematics, and remember that we curl our fingers in the direction of the rotation, and our thumb will give us the direction of the torque. And if you do that for this example, you'll see that the torque is into the page, okay? And that is signified by an X, and the symbol for torque is the Greek letter tau, which is a vector. So technically it's going into the page at the location of the hinge. Okay, so how do you calculate torque? Well, the magnitude of the torque is proportional to that of the force and the moment arm. And this moment arm, by the way, is R. And torque is at a right angle to the plane established by the force and moment arm vectors. So wait a second, what does that mean? This is what it means. Torque is a cross product. It is R cross F. So way back when we did vector review, we said that there would be some cross products that tell us how two vectors interact in a perpendicular fashion, or rather, how much of F is perpendicular to R. And that's what this torque tells us. These are all vectors, so I'm just making note of that. So tau is torque, and it has units of newtons times meters, but it's not work, and it's not energy. Okay? Turns out that there's something you can do with torque to get to energy, but we'll come back to that. So tau is torque. R is the moment arm, which is from the point of rotation to the point of the application of the force, and then F is the force. Now, just as a bit of review, to calculate the magnitude of a cross product, you need the magnitude of each of the vectors times the sine of the angle between them. And again, this is when you put them with a common vertex. But when you calculate when you do the actual cross product to find direction, that's where you need to put them so that F is acting where R stops. Okay? So, also remember that another way to find the magnitude of the torque is if you're given R and F in unit vectors, then we can evaluate this matrix. So if I have R and F as Rx, Ry, Rz, Fx, Fy, and Fz, to evaluate that, I take I hat times essentially the magnitude of we'll write it like this. The determinant, okay, Ry, Rz, Fy, Fz. Then we subtract, I'll write it up here, J hat times Rx, Rz, Fx, Fz, and that was a minus up there. And then we will add K hat, and then Rx, Ry, Fx, Fy. Okay, so we'll get to some examples of this. But first, we're just going to look at a very simple example. Okay, how much force do I need in this situation to get equilibrium? How much force F do I need? So we want to assume that there's no friction on the pulley axle. Okay, so I have three forces. I have this force right here from the 10 kilograms called F1. I have this force right here, F2, from the 2 kilogram. And then I have F going this way. Now, there's three torques that are occurring. Torque 1 is the torque from F1, so it's R1 cross F1. Where's R1? Well, it's a point of rotation to where F1 acts. Okay? And that's 2 centimeters, okay? So it's 0.02 meters, and then F1 is 10 kilograms times 9.8 meters per second squared. And we think about this, which way would F1 tend to rotate this? Using the right-hand rule, we would note that this will cause a positive torque. Okay, so that's roughly plus 2 Newton meters. We'll call that 10 instead of 9.8. Okay, so 100 times 0.02. Okay, then we have a torque from F2, and that's going to be the same thing. We're going to have 0.03 meters, and this time we're going to have basically 20 newtons. So 10 times 2, or 2 times 10. So that's going to give us about, well, let's also think about this. Which way is F2 going to rotate us? It's going to rotate us counterclockwise. That's going to be negative 0.6 Newton meters. And so if we want to achieve equilibrium, then F has to be such so the net torque that we have without F is plus 1.4 Newton meters. So that means that the torque from F has to be negative 1.4 Newton meters. So negative 1.4, well, we'll just talk about the magnitude. It's also at 0.3 it's at 0.3 meters. And then we have an F that we have to do here. Okay? So we just do negative 1.4 divided by 0.03, and that's something like 47 newtons. Okay? So that's the magnitude of the force F. Okay, so what does force and torque have to do with each other? Well, we're going to take F equals ma, and we're going to rewrite it. So we substitute the torque for force, inertia for mass, and angular acceleration for regular acceleration. And we get torque equals I alpha. So tau is torque, I is rotational inertia, and alpha is angular acceleration. Now some things to keep in mind, okay? The magnitude of a torque is R times F, okay? Rotational inertia is mass times R squared, but angular acceleration is actually linear acceleration divided by R. So if you think about all that and plug it into here, you get RF equals mr squared times A over R. Okay, so what happens? Well, one R cancels on each side. These R's cancel, and lo and behold, F equals ma. Okay, so it's not a proof, but at least we're showing you where this comes from. Okay, for example, a 1 kilogram wheel of 25 centimeters is at rest. A force of 0.45 newtons is applied tangent to the rim of the wheel for 5 seconds. After this time, what's the angular velocity? And through what angle does the wheel rotate? Okay, so let's see what we have. So the mass is 1 kilogram, and we have a radius of 0.25 meters. We'll call that a big M. And we have a force of 0.45 newtons for a time of 5 seconds. So what's the angular velocity of the wheel? Well, to get to angular velocity, we're going to have to calculate acceleration times time. Okay? Now omega initial is 0. Okay, so if we want omega final, we need alpha times t. But in order to get alpha, we need to apply torque equals I alpha, the sum of the torques. Okay, now we draw a picture. Okay, and there's only one force acting, but it's acting at a distance r of 0.25 meters. So we can write force times 0.25 meters, and that is going to be equal to I times alpha. Now it's a wheel, and remember that we proved that the moment of inertia for a disk is equal to mr squared. So we're just going to use that, and so m is going to be 1 kilogram, and r is 0.25 meters, and we'll square that. So actually one of those cancels out. Okay, so alpha looks like it's going to be 0.45 newtons over 1 kilogram. And there's a couple units kind of floating around here that we haven't dealt with. And so this is going to give us an acceleration of, whoops, I have to divide that by 0.25 kilograms times meters. Okay? And so that's going to give us about 1.8 radians per second squared. And now we can find the angular velocity because omega is equal to alpha t. So 1.8 radians per second times 5 seconds is going to be 9 radians per second. Okay? What angle does the wheel rotate through in this 5-second period? Well, it's a constant acceleration, so we can use all of our constant acceleration equations. We'll get a different color. So in this case, we have omega final squared is omega initial squared plus 2 alpha theta. We want to get theta. Omega initial is 0. Omega final is 9. So 9 radians per second squared is equal to 2 times 1.8 radians per second times alpha. So times theta, sorry. So this means that the angle that it rotates through is about 22.5 radians. Okay. So next time we're going to do some more sample problems and kind of work through these concepts a little bit more. And we're going to look specifically at how we apply Newton's second law for rotation to systems.